All right, now that Logan's taken the time to walk us through a little whiteboard theory on how the animated sprite class is going to work, let's go ahead and get started. So in this video, he's going to put together a very simple example of a sprite class that supports frame-based animation.
All right, so let's get started. I'm going to begin this with a new project so we can show the creation of the class and then usage itself.
Okay.
So starting a new project, we'll make sure that this project is a Windows game, and I'll call this Sprite Class Test.
Okay.
And then we'll use this project to house the Sprite class itself and provide a very simple test bed. Now, of course, I want to add our two standard folders. That is a textures folder and a classes folder for organization. So we have our textures folder, and we will add also our classes folder.
Almost.
And that was wrong.
Okay.
Much better. All right, now textures, like we've done in the past, we have a working folder that has some example textures in it. We have, as a matter of fact, I guess I could go ahead and open these just to review.
Sure.
In the last video, we took a look at tile sheet, noted the fact that it is a square-ish rectangular grid of individual tiles. Now I have two other textures, a ship sheet graphic, which is a futuristic-looking spaceship, but also divided into a similar grid, though there are a different number of tiles in this sprite sheet. And then also a very simple enemy that has only one row worth of animation.
Mm-hmm. Now, there are differences in these tile sheets for the ship sheet and the enemy.
Right, you can see that here we have 4 by 3, so 12 total tiles arranged in a rectangle. And in the enemy sheet, we have a single row of 4 tiles.
Right.
So we need to make sure our sprite class...
Well, I guess what I'm getting at is we had a little bit of fire flicker coming out of it. There is a difference
you're
between
saying,
each of the...
I see what you're getting at. You're saying that these look very similar tile by tile. The only difference on the enemy is this little bit of fire sticking out at the end gets a little bit higher, then low again.
Exactly. And same thing goes for the other ship.
Exactly. Same thing.
Because at first glance, it's like, hey, they look like
they look static, but yes. The only thing that really changes here is these little lights on the wings and the extent of the fire coming from the engines.
Cool. And that's why we're going to start out with the big tile sheet. Yeah.
We have some very obvious animation going on as this countdown continues.
And if our formula doesn't work right and something gets put in there at the wrong time, it's going to be very noticeable.
Right, because the individual tiles have been noted here. The image generation program that I used was kind enough to put the file name per file for each of these.
Right.
So, knowing that these are the graphics we'll be working with, I'm going to copy them and drop them into our project's textures folder. Then, of course, we'll jump back into Visual Studio. We'll import some existing items from the textures folder as content pipeline files. And that takes care of our graphical assets. Now we'll go up to classes. We'll add a new class, and this will be our sprite class. And this is where all of the fun will take place. So some basic setup. We'll strip off the sub namespace. We'll take out the usings for collections and text, and we'll add usings for XNA various items. So that means a using for Microsoft.xna.framework and also Microsoft.xna.framework.graphics. Alright, now on to the sprite class itself. Inside of the sprite class, we're going to need a series of fields to hold information about the frames, the tiles, and how the animation is working. So let's begin with the first field, which is going to be a texture. The sprite class is going to be based around the XNA texture 2D type. I'm going to make this field public. It'll be the texture 2D field that I'm going to call texture. And again, I'm kind of writing this class in what I would call field shorthand, where I could make this guy private and then expose him through a property. I'm just going to leave him public, though, to keep the code as short as possible. You could very easily turn this into a property to use as an accessor.
Sure.
All right, below that, we're going to have a series of private fields. So we're going to start with tiles X and tiles Y. These will both be of type integer. And we'll jot these down. That is tiles X and tiles Y. As we had discussed on the whiteboard, the purpose of these numbers is to keep a hold account of how many tiles across the tile sheet we have and how many tiles down the tile sheet that we have.
Right.
All right, moving on from here, we have two more variables, tile width and tile height. And these will also be private integers. So tile width And we'll copy that one to tile height. And again, as we had discussed on the whiteboard, we need to be able to track how wide each individual tile should be. And moving on from here, we need to track some information about timing, about frames. So we're going to have another private integer called frame. This will be the current frame that the animation is actually on at the moment. Below that, we'll have another private integer field called frame count. The purpose of this field is to always hold the maximum number of frames in the animation available at all times. That way we know how to loop. That way we can detect that we've reached the end of the tile sheet and we need to begin again at the back at the beginning.
Right.
All right, from there I'm going to drop down two variables for the timing itself, the time that should go by in between individual frames. These will be private fields once again, but they will be of type double. We're going to have the field frame interval, and I'll copy and paste that to frame time remaining. The animation timing system is going to use some code very similar to past exercises where we had to time something using a countdown. That is, we set the time to be equal to the interval, and then we eat away at that using time remaining until time remaining reaches 0, and then we know we've reached the end of our interval. So we'll set up the same kind of timing system here. Now below this, I'm keeping this class generally light on properties, but I am going to add two that would be very useful if this were to be put into use in an actual game. We have tile width and tile height. Now, of course, those represent the rectangle for each individual tile of the animation, but these could be useful externally from this class if one wanted to visually say how wide and high is the sprite just as it is animating on screen. That could be useful in a simple collision system or if you want to check if sprites are overlapping. So I will expose both of these fields as properties.
Okay.
So I'll make public integer properties called width and height, where width is going to have a get accessor that simply returns the tile width. And I'm going to condense this down. I'm going to put all of this on one line to save on the overall number of lines, save on space, since it is a very simple accessor, and it's going to be read-only. So we'll copy the width property, paste it in, and this will make our height property. Again, just exposing these because they would be very useful to have in an actual gaming scenario.
Sure.
Though I guess in theory you could just, oh no, you couldn't, because yeah, exactly, you couldn't look at the texture's width and height, because the texture is the full tile sheet, whereas this provides a useful individual width and height for the sprite itself. Alright, one last property, this time a private property, and this property is going to end up becoming the very heart of the sheet-based animation system. This is going to be a private rectangle property called frame bounds. And it is going to be a read-only property, so we'll have our get accessor. And for the time being, I'm going to leave the code in here generally blank. I'm simply going to return a new rectangle with the intent of coding in an actual implementation before we ever test this class. So we'll be coming back to that once we have more of the methods in place. And really, that takes care of all of the fields, though I do want to point out one thing real quick about some of the fields that we have here. Keeping both tiles X, tiles Y, width, and height as individual fields. As you'll see when we build the constructor, some of these values can be gotten from other values. That means we'll actually be calculating the tile width based on the overall sheet width divided by the number of tiles in X. So that means these fields don't necessarily have to be put down as fields, but it does save on calculations for every engine tick to simply remember that value. So
yeah,
it's kind
as opposed to performing a calculation every single cycle.
Exactly. So we'll do a trade-off where we use just a little bit more memory and then use fewer CPU cycles per frame. And that really brings us into the methods themselves. So what I'll do here is I'll skeleton in the constructor and the methods for the class, then we'll immediately turn back around and drop down an implementation for each. So we'll begin with the constructor. So this will be a public constructor. And then we have several parameters that we need to feed to it. The first parameter is a texture2D, which we will call texture. The second is the tiles x and tiles y values. Let me jot these down. We'll have int tiles x and an integer for tiles y. What it comes down to is, in order to describe the grid layout for each of these tile sheets, we need to tell the sprite class one of two things when we're creating it. Either how many tiles in x and y are there, or how wide is each tile in x and y. I opted to go with tiles x and tiles y being given because it's easier to visually look at. If you look at a tile sheet, it is very easy to count how many tiles wide it is and how many tiles high it is. Generally, you would need an image editing software to measure the tiles in pixel width. So this makes a more human-friendly entry method for making the sprite. Let's see. Now to finish off the constructor, we have a few more things. We need to feed in a frame rate. So we'll feed this in as a double. And then we need to feed in the total number of frames, so the frame count. And that will make up our constructor. So I'll move on to the skeleton of the two remaining methods, that is update and draw. So we'll have a public void method called update, and update is going to take in a game time, which is how we'll know how much time has passed for each update of the sprite class. Then the final method will be a public void draw method. And draw is going to need to take in a sprite batch to perform the actual draw call. And then there's one other thing I'm going to feed into the draw call. You'll notice that up until now we have no positional information for a sprite. I have specifically left position out of Sprite to make it a little bit more generic and generally applicable. The idea behind Sprite is that it is in charge of frame-based animation and very little else. So that would mean if you wanted to position these as game objects moving around the screen, they would need a supporting class like an actor or an entity that can move around and be processed on screen. And then we'll just look at the sprite to tell what frame of animation in order to draw it. So that means positional information is going to need to be fed in from somewhere else. And we'll take that information in at the draw method as a vector2, which I will simply call position. And that takes care of our skeleton. Let me build and make sure that there's no simple errors, though I guess a build is just a very preliminary check here. But amazingly enough, no errors, so we can now turn around and turn our attention to the implementation of each of these methods, beginning with the constructor. The main thing the constructor is going to do is simply initialize all of the fields based on the information taken in. That means doing things like remember the texture, so this.texture will be set based on the parameter texture. We'll set our tiles x and tiles y equal to their parameters values, so tiles x. You can copy and paste that line a few times so that we can remember and save the value for tiles y. Then we need to take a look at the tile width and tile height. So tile width, what is tile width going to be equal to? Well, we're not feeding that in directly, but we can figure it out knowing that the texture is going to have an overall width, and we've specified how many tiles in x. So we can say that the tile width is going to be equal to the texture's width divided by tiles x. So the incoming texture dot width divided by tiles x. And then we can run pretty much the same calculation for height, where we look at the overall texture's height and divide that by tiles y. So moving on from here, we need to drop in things like the frame count and frame interval. The frame count is very easy. We just drop in the parameter directly. Now here's something interesting. Let's look at the next field coming up is the frame interval. Now notice that we're feeding in the speed parameter as frame rate coming into the constructor. And reason being is that just makes more sense in the gaming context. You generally think of things in frame rates, like a modern game would run at 60 frames a second. Tile animation that isn't set up for full speed, or maybe if it was set up for only quarter speed, would be 15 frames a second. This is easier to comprehend and think about than intervals like 0.016 seconds or 0.033 seconds. Now that does mean, though the smaller value, the 0.33 seconds or 0.16, is more useful in the moment-by-moment time calculation. So what we'll do is we'll convert between the two. The human-friendly frame rate will be converted into the machine-friendly time interval. And we'll do that by simply dividing, or getting the reciprocal of the frame rate. So we'll take 1 divided by frame rate. That way, if we got a frame rate of 30, we should have 1 divided by 30, which should give us, I guess, something like 0.333 and so on. I guess I could calculate that so that I don't have everyone running the calculation on their own and getting a different result. But to look at 30 frames a second, 1 divided by 30 would give 0.0333 seconds as the interval in question. So that way we automatically do the conversion right there. Alright, one last field, and that is the frame time remaining. This is simply to initialize frame time remaining so that the animation doesn't advance off of its first frame until the interval has expired. So frame time interval will begin, or excuse me, not frame time interval rather, but frame time remaining will be set to frame interval so that the first frame can survive or can show for its full duration before continuing.
That's right.
Alright. Now, before we move on past the constructor, there's one other thing I want to address, and that is the frame count does not necessarily have to be given. We can figure out the frame count on our own in code as long as every square within the tile sheet is filled. We can simply multiply tiles x by tiles y, and that gives us the total number of tiles. And that can be convenient if we know the texture in question has all tiles filled. So I'm going to overload the constructor and provide another constructor that allows us to omit the frame count. So I'm going to put in a public sprite constructor, and I'm going to copy most of the old one. As a matter of fact, everything up until frame count. And then we'll jump down a line, and we'll make a call to the first constructor that we had made. And in that call, we'll specify, basically we'll just pass everything along and then perform the very simple calculation at the end. This will pass along texture, will pass along tiles x, tiles y, the frame rate. And now to figure out the frame count, we simply multiply the given tiles x times tiles y, and that gives us our frame count, and gives us the option of omitting the frame count if we wish when creating a sprite class. I'm just going to leave the brackets empty at the very right hand corner since there's no actual code needed in this constructor. Alright, that takes care of constructor stuff, so let's look at update and draw. Update is where we're going to need to worry about that frame variable, making sure that it increments frame by frame and then restarts after we get to the last frame of the animation. So down here on update, the first thing we need to do is look at the time frame remaining and see if that has run out yet, meaning if that has tripped a frame change. So we'll take, and really I guess before we even do that check, we need to make sure that frame time remaining is continually eaten away at, continually decremented as time passes. So that would be this dot frame time remaining is decremented by the game time, elapsed game time that has passed. So elapsed game time, we'll look at that in total seconds, and we'll use that to decrement frame time remaining. Then we can do a check, see if this dot frame time remaining is less than or equal to 0, in which case we have run out of frame time remaining. It's time to flip the virtual egg timer, if you want to call it that, and also account for the fact that the frame has now advanced. The frame advancing is simply a matter of taking frame and incrementing it. Now, we have to be careful with incrementing it, because if we've just exceeded 8, if we've gone on to a value of 9 here, we need to make sure we modulus this to restart it back at 0. So the very next thing we'll do is make sure we take this dot frame, modulus equal the overall frame count, to make sure that if we have gone over, we then reset back to frame 0. And then one last thing we need to do is to reset the time remaining back to the initial interval value. And then this will start the countdown process over again. And really, that's all there is to update.
Yeah, it's really straightforward.
And very similar to past timing methods. All right, now we can move on to draw, which is going to be even more simplistic. The call to draw will simply use the sprite batch and the position to draw a piece of the current texture. So our call to draw will include the current texture. We'll use the given position, vector 2, for position here. And then we're going to jump down a few overloads because we do want to specify a source rectangle.
That's right.
That source rectangle is going to be given by our frame, I think it was frame bounds property. That frame bounds will return a rectangle which describes the current tile of the animation. And then the color will simply be color.white because no facility for color modulation is going to be given. And that's it. Though that does mean we need to turn our attention to frame bounds and make sure that that can perform the proper math in order to pull a tile out of the tile sheet. So now we'll move back up to our frame bounds property. I'll take out the simple return and we'll put in the actual math necessary here. We'll need two integers, an integer x and y. X is going to be set by the current frame modulus the tiles x. Now, of course, that would give us from 0 to the number of tiles, so we need to take that value and then multiply it against tile width. And I guess each of those could have the this keyword in front of them. I'm actually going to leave the this keyword off just to make the formula a little bit more clear. But once you've got a handle on this, then you could very easily just go back in and add that. And that means we can look at the y value, which is again going to be based on frame, but this time will be frame divided by tiles x. So every time we advance a row, then y will increase. Then we'll take the overall value from y and multiply that by tile height. With this x and y value, we can begin building a new rectangle. So let's start a return statement. And we'll return a new rectangle with an x and y value given by the variables x and y. Width is very easy. That is, of course, the tile width. And y is the tile height. And that describes our new rectangle used for finding the current frame bounds.
Beautiful.
So let me build and ensure that there are no errors in the class, and we can turn our attention to the game class and try out our new sprite and make sure that the animation is working. So over in game, let's make a few fields inside the game class itself. We'll make a sprite batch and then a field to hold an instance of an actual sprite. So the sprite batch field called sprite batch, and some spelling, and then a sprite class called sprite. Then we could move down to the initialize method and create the sprite batch itself. So our sprite batch will be equal to a new sprite batch with the current graphics device. Now I'm going to hold off on creating the sprite itself until we get into the load graphics content method, since sprite's functionality and even constructor are based around having a loaded texture. There's not much we can do usefully with sprite until we have the texture loaded. So now we'll jump down to the load graphics content section, and here I'm going to make a local texture variable of type texture 2D. I won't even hold a reference to the texture itself in the main game class. We'll let sprite worry about that. Though I will make a variable here just to ease the loading syntax. And so this texture will be equal to the standard content.load, so we can load in one of the texture assets for the project. So we'll load in under the folder textures, and the first graphic we'll look at is the tile sheet. So we'll load that graphic in. Now we can turn around and create the sprite. So we can see that our instance of sprite will be equal to a new sprite. Now we have a texture to feed into it. And as we had counted before, as a matter of fact, I could bring that graphic back up since we will need to know how many tiles in X and how many tiles in Y to satisfy the constructor. So we could reopen our title sheet and count, let's see, 1, 2, 3, 4, 5 across, 1, 2, 3, 4, 5, 6 down, so 6 in Y. So that will be tiles, let me bring up the parameter list, tiles X of 5, tiles Y of 6. The frame rate, I'm going to begin with a frame rate of 2 frames a second. Very slow so that we can count the numbers incrementing.
Okay.
And I'll leave off the overall, or I will not specify a number of frames, we'll let that be generated automatically, which we know should cause a small flicker with the current graphic since we need to omit the last frame. But we'll leave that there for now, and we'll put in the rest of the code so we can test our draw functionality. That means inside of update, we will call upon the sprites update method, feeding it game time. And then inside of draw, let's set up our sprite batch to begin drawing. And while we're at it, we'll throw in a call to spriteBatch.end. And then we can look at our sprite instance and tell it to draw. And we'll feed in the current sprite batch and a position. I'm just going to put in vector2.0 since I don't have this animated or moving anywhere on screen. We'll just draw it in the top left corner of the screen. So with all of these things in place, let me build and make sure that there are no errors, and then we can try running the game. And look at that.
Nice.
We are advancing in time, frame by frame, as indicated by the counter at the bottom, and we can see the animation itself continuing.
And we should get a nice blue splash in a second.
So as we're hitting 28, last frame, flicker, and then return.
Okay.
And that blue color matches the blue color of the background. So let me change the background color here to something like slate gray, and let me up the frame rate to show what that's actually looking at. The original frame rate that this graphic was designed for was 30 frames a second. So this way we would see a smooth animation. And we do see a smooth animation, but every time we hit the last frame we get that flicker of blue because we're letting the sprite automatically pick the number of frames, which means it's coming up with 5 times 6, giving 30 frames, but we know from looking at the graphic that we have one less than 30. We have 29 actual frames, 0 through 28. So that's why we've given ourselves the ability to specify that if we want. We know that there are in fact 29 frames, not 30. So if we specify 29 and rerun, now the animation loops properly and we don't see that flicker of the invalid or empty tile.
Very nice.
So that has verified that our sprite is in fact working. All the frames are advancing properly. So let's play around with those other graphics. Let's look at the ship graphic and show what that would look like animated. So let's put in ship sheet. Now I'm going to change these values back to 1 by 1 for a moment, and what this is going to do is tell it to pretend there's only one tile overall. This means that when I run, actually let me change the number of frames down to 1 as well. That way we are only animating for that single frame. This makes it easier to count. So we know that looking here we have 1, 2, 3, 4 wide by 1, 2, 3 tall. So that means our tiles X should be 4, our tiles Y should be 3. Our frame rate, I'm going to slow this to 15 just because there's fewer frames to work with, and I'm going to allow the frame count to be calculated automatically. And now we have the ship graphic with the engine animation playing properly.
Excellent.
And we could do one last test with the enemy sheet. Since we know that it's not going to be the same values, I'll simply take these all the way back to 1 by 1. And there we can see we have 4 across and only 1 row. So it means we could set our tiles X to 4. And now we have a nice, smooth animation.
Very nice.
And though if we manage to mess up these values to something they shouldn't be, we can get really interesting tracking errors. As a matter of fact, let me take this back to the full tile sheet. I just want to show this because it's a little bit interesting and actually reminds me of a VCR that's that has improper tracking set on it. Like, what if we swapped 6 by 5, knowing that it's supposed to be 5 across and 6 down? What happens if we swap these values? Well, now it's as though we have an improperly tracked VCR. We're actually looking at a tile width that is too tall, too narrow, and doesn't match the individual frame. So we're looking at the wrong segment frame by frame. So this is the result that can be expected if the frame is improperly aligned using the tile's X and Y value. Of course, the proper values were swapped, 5 by 6, and in this particular case we have to give a frame count of 29 to avoid the blue frame. And there we have our nice smooth animation. So really that covers the implementation that I wanted to accomplish in this video.
Okay.
Is there anything you wanted to add?
No, great job. So with that, that's going to wrap up this video. Thanks a lot.